Hello everyone, this is Dr. Me again, ECE410 Power Electronics, class number 9. Today we're going to talk about buck boost converter. So what is buck boost converter and what are the equations to lead the design of a buck boost converter? That's the topic for today. So let's get started here. So we have discussed other converters in the past. Let's see, can you take a look at them and see what is a direct converter, what is indirect converter. Direct converter means that when you connect switch, one of the switch, that means you're connecting between input and output. So if you look over here, if you connect this switch over here for this converter, it's a buck converter, right? Then you see that your input and output directly connected, right? And if you do this one for the boost converter here, if you connect this one, your input and output directly connected. But if you look at this one here, if you connect this one, right, input doesn't connect to output. And also, if you connect the other one, take this one off, and connect the other one, other switch, that also doesn't connect input to output. So if input and output can be connected through a switch, this is called direct converter. If they are not connected through a switch, it's called indirect converter. So that means these two are direct converter. And this one over here is indirect converter. You cannot connect input and output by using a switch. All right. So that's that. Then talk about something else here, before which be very important for us to know. So look at here. For this buck converter over here, this side has a constant voltage. This input has constant voltage because you're connected to the voltage source right there. Constant voltage. Right? And look at what's happening output. This is the inductor here, right? This inductor will keep the current constant. So that means at the output, you have a constant current. So constant current at output, right? So that means buck converter converting or connecting a voltage source to a current source, right? So constant voltage in the input and constant current in the output. So connecting voltage source to current source. On the other side over here, for this one here, you have an inductor in the input. That means you're going to keep the current constant, right? And you have a capacitor here that will keep the voltage constant on the output. Right? So that means you're connecting a constant current source to a constant voltage source for the boost converter, right? So that's important to derive our buck boost converter. We're going to get there soon. All right? I hope you understand what I'm talking about here. So now, as a buck converter, I said you have a constant voltage source in the input, output is constant current source. So you can just convert that, the schematic diagram with this one, with the constant voltage source and constant current source. And boost converter has other way around. So now, if you want to combine them together, you can flip the output here, flip the whole thing over here. So look at the polarity change. You can see the polarity change over here. Right? So then both have the same direction for the current. So we can now combine these two two current sources together because the parallel current source could be combined, right? So then we have one current source over here. So then we have also this switch over here. These two switches doesn't do any good for the conversion. So you can take them off. So if you take them off, your diagram look like this. Right? So that means on the both side you have your voltage source, but in between you're going through a current source. So that means you're not connecting voltage to voltage source to basically violate your KVL. So you're going through a current source between the conversion. So buck boost converter basically combining your buck converter and boost converter together to get the buck boost converter. All right. So this one over here is basically an inductor. So that's what over here. So that is your buck boost converter. So this switch could be a forward converting, reverse forward blocking, which is basically any MOSFET can do that. And this would be forward converting, reverse blocking, any diode can do that. So this would be a MOSFET, any MOSFET can do that, or BJT, or even IGBT. This is a diode over here. All right, and this is an inductor. That's the basic things over here. And also to keep the voltage constant over here, I can use a capacitor there too. So that is your boost converter. So now if I draw it with the circuit element over here, that's your buck boost converter. V in, V out, right? And this is the V out over here, right? Then this is L, this is your VL over here, right? And the current going through this, not the red one, green one. Current going here is IL, right? So that's your buck boost converter. So now this switch over here, switch 1 and 2, they're complementary. That means if you add them together, the one, that means only one can be on at a particular time. So now when switch 1 is on here, so your inductor is getting energy from the source. That means inductor voltage over here would be basically the V in voltage with the amount of time your switch 1 is on. And when switch 2 is on, inductor is connected to the output voltage, so it will be output voltage, and with the amount of time your switch is on. So if you combine them together, your transfer voltage over here is Q1 V in minus Q2 V out. And if you try to find the power here, if you multiply by current, that current would be the inductor current. So that is right here, right? And we want a lossless inductor. We don't want any power consumed by the inductor. So that be for ideal case, the power should be zero. Inductor power should be zero. So now it's the same one here. So if we say that on average over here, if this is what the switch 1 is on and this is switch 2 is on, and power, average power, that should be zero. So that is, this should be equal to 0, right? If that should be equal to 0, then your V out would be V in D over D1 over D2, right? So, and D1 plus D2 is 1. So D2 is 1 minus D1. So over here, then your V out is V in D1, 1 minus D1, right? So that's the equation for the output. And this output is, this is the positive side over here, is reverse. So this output with the common ground, this output would be negative, right? So that's the output voltage for your buck boost converter. And that is right here. You can see that. And also with the polarity reversal, so V out, as I said, would be negative, V in D1, 1 minus D1. All right. Sometimes we use D1 equal to D. You can also see that sometimes we use that, right? So now you can also get the same result. You also can get the same result, this one here, using energy conversion we used before. We can use the energy conversion formula, also achieve the same result we have over here. Let me give you a head start on that. Let's see here. So for the buck boost converter, if I do that, you have done it before. This is nothing new for here. You have done it in beginning of the class, right? Right? So over here is L, is the VL, positive, negative. So when switch 1 is on for time D or D1, what do you call it? So it's 0 to DT. When switch 1 is on, as I said, 1 is here and 2 is here. 1 is on, V in equal to VL, right? So it will be V in, let me go back and use the actual equation here. So is VL IL dt, and switch 2 is on, 1 is off now, should be dt to t here. Again, VL, IL, dt should be equal to 0, right? Total energy across the inductor should be 0 over the period. So now, when switch 1 is on, your VL is actually V in, right? So I can replace that over here. So V in, IL, dt, plus when switch 2 is on now, which 2 is on now here, your VL would be V out. Your VL would be V out. So it would be V out, IL, dt should be equal to 0, right? So if you now take the integration over here, V in, dt, IL, plus V out, IL, t minus dt should be equal to 0, right? So your IL and t will be the common factor will be out here. So your V out would be negative V in d 1 minus d. So the same equation where d is equal to d1, right? So if you plot it, this is what happened for the voltage over here is goes up, up, and up. So if you look at here, if your d is 0, d is 0, right? That means what? V out should be 0, right? If you're so V out should be 0. If d is 1, look at here, V out is infinity. Can you see that? If d is 1, V out could be theoretically infinity. All right. So now we have seen that. This is basically, as I said, is basically inductor here. And so what's the relation between inductor current and the other current over here, input and output current? So again, I'm going to draw this same figure here to make sure that we are graphically can see it. Right? So this is your IL, right? When switch 1 is on, and this is switch 2 here, when switch 1 is on, your IL is basically I in. So I in is coming here, right? I in. So switch 1 is on, your IL is basically I in. So that means right here, so I in is D1 times IL. D1 is what time is switch 1 is on. And when switch 2 is on, if you put the 2 on here now, so your IL is basically your output current now, right? Output current here. So that is right here. The output current is D2 IL. So now if I add input and output current, so that is the equation right here. So that means D1 plus D2 is 1. So IL. So IL is input plus output current for the buck boost converter. So that means your inductor should be rated for both input current plus output current. And if I do the same thing for your buck converter here, it's a buck converter, right? So your I out is here, it's average I out, your ripple should go to the capacitor. So this is IL here, right? So for buck converter, for the buck converter, your IL is I out. Can you see that? For buck converter, your IL is I out. That means the inductor should be rated for output current. For the boost converter, if I draw the boost converter over here, so now this is your I in over here, average I in, and this is also the IL over here. So you can see that your IL is average IL is equal to average I in, right? So that means for the boost converter, your inductor current is input current, so inductor should be rated for the input current. So this is the three different, and for the buck boost converter, your inductor current is input current plus output current average, so you should be rated for the both input and output current. All right. Okay, so now again, I'm going to draw the buck boost converter again here to make sure that we can see it graphically. Okay, now this is your V out, even that is other way around here, and this is your V in, right? So now, if your switch 2 is on, your switch 2 is on, 1 is off. So 1 is off. That means over here, your negative V in comes in over here, right? And over here is positive V in. So that switch over here need to be rated. The voltage across the switch is now V in plus, sorry, V out. This is the V out. So now over here is across the, when it's off, across the switch, you have V in plus V out, right? So that's that. Then look at the other one now. Oh, what I'm doing. So now, okay. So now this one is on, this one is off, right? So that means at this point over here, you have again positive V in. At this point over here, you have negative V in. Also, both voltage comes across the switch, right? So that means your switch should be rated for V in plus V out, right? Input switch be rated for your also inductor current, right? It carries inductor current, input switch. Output switch also carries inductor current. At the same time, there should be rated for the input plus output voltage, all right? So that's all for this lecture. Then we're going to the class, we're gonna solve the problem. We have 3 different problems here. So we're gonna solve the problem in the class. And I'll see you in the class soon.